All right, let's get going. Okay, so we're going to talk today about visualization of deep networks. It's an important topic because the networks are, poorly understood generally, and visualization gives us a window into what's happening, gives us ideas about optimizing networks and what kinds of representations they're already computing. So we'll get into that in a moment. Last time we looked at recurrent networks, which process sequences, and they have a notion of time. And as a sequence of symbols xt comes in, you output a corresponding yt, but also you remember a hidden state ht that becomes the input state for the next time step. And they have a variety of applications. They can be used either on the input or the output side. And specifically, we looked at caption generation for images, where we take a latent vector from near the output of a convolutional network, and we feed that, we map it into the hidden dimension space for a recurrent network. And then the network generates, if it's in generating mode, it generates a caption. We feed in the start token first into the recurrent network, and it outputs a word. And then we take that word and feed it back in as the X input to the network. And we use the hidden state from the previous step as the hidden state input, and it will generate another token. And because the network's been trained at training time to look at images in this fashion and then output meaningful captions, when we run it at test time, it'll also tend to give pretty good captions. Okay. So a difficulty with the vanilla recurrent network is that it was always applying some kind of linear transformation to the hidden state. So, it's essentially scrambling the hidden state each time. A lot of the time, though, if you're doing recurrent operations, you want to remember something. You might remember the level of parentheses in a piece of C code, or you might want to remember the characters that are in a play. So it's better if you can have some kind of recurrent input that's not being changed, or at the very least, it's only being sort of turned on or off. And that's what the C recurrent state is for an LSTM. So the LSTM has a general recurrent state down here that gets transformed by a linear weight map, but then this special memory state up there, and the memory state's only gated on and off by this gate function here, or a new hidden state is introduced from that logic in the middle. And that design was proven to be very effective at generating very complicated structured text in a variety of applications. And already, last time we did a bit of visualization of what's going on in these networks. And if you look at the C state, so the individual components of the C vector for various types of problem, you can often find a C that's interpretable just by plotting its activation level across the input. So here red is highly activated and blue is weakly activated. And you can see that this one appears to capture code depth. So the more nested the input is, the more activated the cell is. Excuse me. All right. So that was last time, and a reminder about the midterm coming up a week from yesterday. So it's an evening midterm, 7 to 8:30. We had to book multiple rooms to fit everybody in. That's the allocation of rooms. Should be plenty of space in each room. And it's a closed book exam with one double-sided set of notes. And if you're in an exceptional situation, if you need time and a half or double time, we will be contacting you separately, or we probably have already. But these are the default rooms. So just take a look at this. It's also posted on the main B courses page. If you click on midterm locations, it's in the schedule. You'll see the same information. And we have a review session on Monday, 8 to 10 in Pimentel. Any questions? All right, and the midterm would be similar in content and design to the previous ones that are posted. And the geoscience will be giving some solutions to the most recent one in the review session. Okay, so moving on, if no one's got any questions. So one of the most general types of visualization is embedding, where you take high-dimensional data. Could be of many different types, could be weights or activations or data itself, data points. And you somehow map it into a two-dimensional space, preserving the metric properties of the data. So in other words, by metric properties, I mean if things are close together in high dimensions, you want them to be close together in 2 dimensions when you plot them. And embedding is the process of making a 2-dimensional plot. Once you have data embedded, you might additionally do some clustering or labeling, such as on the right there, but that's a separate process. The embedding is just taking high-dimensional data and making it into 2-dimensional data. Okay. So the general idea, there's a particular method that's widely used with neural networks, which is called T-SNE. And the idea of this, rather than other projection methods like PCA, you can use principal component analysis too, which is a linear projection. And a weakness of linear projections is that they're more likely to preserve large distances than small distances. In other words, the L2 error is higher when things are far apart, and that's actually typically the opposite of what you want. If you have a cluster or a set of points that are closely spaced in high dimensions, you want that to be closely spaced and appear like a cluster in 2D. And you don't care as much where that projected cluster is relative to the other clusters. All right, so you're willing to move things around and kind of violate the large distances from the original space, as long as you get the small distances. So T-SNE is stochastic neighbor embedding. And it's a method of doing this, basically preserving closeness rather than a long distance when you do a projection. All right, so the idea is things that are close in high dimensions, when they get projected down, will be close in 2D. And this, for instance, this, for instance, is an embedding of MNIST data. So the high-dimensional data is actually pixel images of the digits. So MNIST, if you remember, it's handwritten digits from letters, the post-zip codes from letters. And so there's 10 clusters of state, of representation. So in high dimensions, the images, I forget what they are, about 30 by 30, something like that. So they're quite high-dimensional. They're 1,000-dimensional data, and hard to work with, hard to visualize what they look like. On the other hand, you expect each particular digit, like 0, 1, etc. Each digit should be clustered together, right? You should see, when you project them down, that they're close together. So that's what T-SNE does. Okay. And in fact, T-SNE, it's kind of a probabilistic model. It defines distances in high dimensions and low dimensions. So the high dimensional points, the original data set points, are the xi's there in 1,000 dimensions in this case. And the yi and yj are the corresponding projections. So almost always in 2D. So y and yj, yj are in 2D, xi, xj in much higher dimensions. So the idea is we somehow want to preserve similarity and closeness. So we define this value, which we think of as a probability, actually. And it's kind of a normal distribution based on the distance between the points. Does that make sense? So the probability, it's a normalized normal distribution. So this is the distance between the 2 points the denominator is the sum of distances for other points. So it's almost like a softmax, I guess. Anyway, so that gives you a value that's going to be quite large if the points are close together, or if the points are identical, right? The numerator will be 1, and presumably the denominator will be somewhat less. So this probability, actually the way it's defined, it's not strictly a probability because it could be greater than 1. But it's kind of strange. They probably should have considered k possibly equal to I. Anyway, it's still, the operation you do with it actually turns out to be well defined anyway. Anyway, so that's the probability of two things being neighbors. So neighbor means close together with some Gaussian distribution, normalized. And then downstairs, we have exactly the same formula except for the sigmas, except for the normalization constant here, for the y's. And all right, so probabilities are highest when points are close together. And this one, this one has a kind of scale factor sigma, which depends on how spread out the data is and how many, the approximate distance to the neighbors of x. Because if you think about it, high dimensional data has an arbitrary scale factor, and the sigma I squared captures that. On the other hand, when you project the data down, you can afford to project it in roughly a unit, or a -1 to +1 square. And the normalization already takes care of getting it into that square by setting sigma effectively to, I guess, 1/√2. All right, so yeah, and as I said, there's a little bit of heuristic stuff that happens, which we won't talk about, but you adjust that sigma to be a reasonable scale factor for the original data set, so that you end up with a modest number of neighbors for each point xi. All right, so anyway, xi are the input and yi are the output of this. Is that clear? You're trying to project each point xi down to 2D. So these expressions especially for q is symbolic. It's a function of the y's that you're going to optimize. So given that, assuming p of j given I and q of j given I are probability distributions, which you probably need to consider all the values of k to do that, but assuming they are, you can measure the divergence between probability distributions by, by this formula here. This is a KL divergence formula. It's a measure of how different two distributions are. And you'd like the distribution P and the distribution Q to be as close as possible. In particular, you like the Q probability to be large, which means points are close together whenever the P probability is large. And you don't care as much when they're small. So anyway, so this is the formula. So it's like a loss as a function of the position of the points yi. That's our model parameter, all of the points yi. So this is a loss. We can compute gradients with respect to the parameters, which are the points yi, and use SGD or whatever we want to use to minimize that divergence. Does that make sense? And the end result will be getting basically, some sort of embedding of the points, such that the points that are nearby upstairs and nearby downstairs. Okay. Now, KL divergence, hopefully most of you have seen it before, but just in case, if you could grab your clicker. Hopefully most of you remember this from 189 or somewhere, probability course. We'll review it quickly here, but it's going to be cropping up again in various places in the course. So let's take a simple case where we have a discrete probability distribution. So there's only one index. Then the divergence, KL divergence between P and Q is defined as the sum over P of log Pi over Qi. or if you like to think about it alternatively, it's expected value over the probability distribution P of log of Pi over Qi. Does that make sense? Okay, so there are a bunch of properties that metrics or distance functions can satisfy. One of them is symmetry. Just KLPQ is the same as QP. Oh, I'm sorry. Yeah, sorry. All right, sorry about that. So one is that the measure is symmetric, so distance of PQ is the same as distance of QP. Triangle inequality, you can read it there. You've probably seen it before. The third measure is just saying that the distance measure is 0 if and only if the true probability distributions are the same. For technical reasons, you have to say almost everywhere because things are not defined where one of them is 0. Or option D is all of the above. Excuse me. So if you could just click in a choice. And we'll see how we did. All right, all right, cool. So it's a contest between C and D. So let's look at some of these. So probably pause the other one to go away. So symmetry, actually no. If you can see, well, first of all, the formula is not symmetric, right? P shows up here and not, Q doesn't show up there. And also P and Q have different signs. So in fact, it's not in general symmetric. In fact, almost any example, just plug in any example of the distribution, you'll get different values by reversing. So what about, triangle inequality? Well, same deal. You can plug in simple examples, almost any example. Actually, you have to work a little bit harder here. I shouldn't say almost any example will fail, but a large class of examples will fail the triangle inequality, such as this one. Okay, you can just plug in the data and figure out that it's not satisfied. So it's actually not a metric. It's called a pre-metric. Anyway, it does, however, satisfy this property, which is that the measure is 0 if and only if P and Q are the same almost everywhere. And also, it's strictly non-negative. So it's 0 if and only if that first condition is true. Everywhere else, it's positive. Is that clear? Any other situation implies that P is not equal to Q. And that will give a positive value for DKL. So it's still a pre-metric, which means that the equality operation is transitive, which means you can group together different probability distributions that are equal to each other almost everywhere. And in that way, you can partition up the set of distributions into equivalence classes. So it's not quite, that's an important property. It's not as strong as a metric, but it's still pretty useful. Okay, and that one's wrong for the reasons just given. Okay, so let's keep going. So going back to t-SNE, we're going to minimize this KL divergence between the sort of probabilities upstairs and the probabilities downstairs, and optimizing. You can, in fact, use stochastic gradient. That's why it's called stochastic neighbor embedding. All right, is that intuitive? Hopefully it's good, yeah. So to compare it, for instance, to linear embedding, if we took the MNIST data again, so this is the images themselves. At the top, they're being embedded with t-SNE, and you can see that you get effectively disjoint clusters in 2D for different digits. If you try to use PCA, again, because it's optimizing large distances instead of small ones, it tends to produce, or it does produce, this mixed up plot downstairs. And in fact, any linear method will have that same limitation. All right. Just to quickly be clear, t-SNE is not a clustering method by itself. It's an embedding method. So if you want to produce a clustering, you need to run a secondary clustering algorithm on t-SNE. And generally, dbScan, for instance, is a better approach than, let's say, k-means clustering. Well, the idea is that dbScan is density-based clustering, which means that it extends a cluster by adding points that are very close to the existing points in each cluster. Does that make sense? So it's capable of producing very elongated or non-spherical clusters. Whereas k-means, every cluster in k-means, on the other hand, has a centroid. And the elements of the cluster are the things that are closer to that centroid than some other centroid. So that means when your data looks like this, k-means is going to tend to do a bad job because it's basically going to cover the actual data with spherical regions, which don't correspond very well, arguably, to the natural structure of the data set. That make sense? All right. So t-SNE is the first step, and then you probably want to use the density-based clustering if you want to turn the high-dimensional data into clusters. All right. Excuse me. Well, this is a technical point. t-SNE can be done very efficiently in time that's roughly linear in the number of points, and it can run to millions of points or millions of images. You can kind of actually do t-SNE of ImageNet data. Well, this is almost ImageNet data. If you take the 4,000 dimensional output of a AlexNet as the features space, you can use that to embed all of the images in ImageNet. And can't really see them very well, but they're kind of similar. Let me see if I can zoom in. Let's just zoom in here a minute. Oh, no, I don't want to do that. Shoot, what do I do at this point? Can I leave that behind? All right. Sorry, I shouldn't have done that. Okay. All right, so I'm going to have to save this and restart. Sorry. All right. Starting again. No, I don't want to do that. Trying one more time. Okay. Okay. So here we are. So, excuse me. Images are placed nearby if they're seen in representations are close. And I won't do it here because it'll mess everything up, but you can zoom into this photo and see the component images and see that they're actually quite similar to each other. Perhaps a more interesting application of t-SNE is you can actually embed or cluster the policies of a game playing policy, such as this one that's playing Breakout. And so if you take the agent's policy network, which is a deep network, we'll be analyzing these kind of problems later on in the course. You can take the raw activations of the network while it's playing the game and cluster, or sorry, don't want to say cluster, but embed them into a planar layout like this. And then, for instance, color them by score or some other measure. You get this kind of plot. And the clusters that t-SNE finds actually do correspond to distinct policies or game states, and or if another way to put it is strategies for particular situations in the game. And that analysis can help you find problems with the policy, such as the agent having just a few blocks left on the game board and not being able to hit them. All right, so any questions about T-SNE before we move on to CNNs? Okay, let's go. Yeah?
For the digits case, what if you just put the raw data to T-SNE? Would it give a clear clustering?
We did, that was the raw, you mean the image data? That was the raw data for T-SNE. The very first visualizations were just the digit intensities. Yeah.
People use that later for network outputs.
The second, so the very first visualization we saw was just the 2D embeddings of the actual digits from MNIST. The one we just saw a couple of slides ago was, instead of the raw images, it was the output of the CNN of an AlexNet, the 1,000-dimensional output. Those were mapped into the plane, and then the actual images were kind of overlaid on them. And the idea there is that the latent representation that the network computes is much more like, these images are really similar at high level versus at pixel level, you'd be getting things with similar white backgrounds or, day-night backgrounds, but not the same content. Okay. So visualizations are important for understanding networks, and especially convolutional networks. Convolutional networks, because they're working on images, often give us ways of understanding the network that are interpretable, again, because they can relate back to parts of the image. So we'll explore some of these ways of understanding convolutional networks next. All right, so here are some images. There's an AlexNet once again, and that's the RCNN paper, which finds regions in the image. And basically, the regions are determined by a region prediction subnetwork that's trained to find those regions. And if we go all the way back to interpreting AlexNet, the very simplest thing we could do is look at filter weights. And that's, in fact, what you can do. So in the first layer, so these are the weights shown in RGB color for the filters. These are the filters down here. They're typically 11 by 11. They're applied to the RGB values of the input image. And so each one of them does have color. And they're shown as a grid here because of the depth going this way. What is it, 48 or is it 96? 96. So there should be 96 images in this grid corresponding to the 96 filters in the first layer of the CNN. Is that clear? And they're, just to explain the color, they're sort of false colored positive and negative, so gray is 0, because filter weights can be negative. So negative will appear as black, positive will appear as white. Color is, they're normalized at 0, so a positive green is higher green intensity than average. That makes sense. Okay, so that works reasonably well, and you can see that there are various types of edge filter. In fact, they're fairly high order. They're capturing oscillation in particular directions. Some of them are actually capturing texture. But they have a specific orientation, horizontal, vertical, or diagonal. Now, unfortunately, as you go up in the network, this doesn't work anymore because there are nonlinearities between the first layer and the second layer of convolution. So whereas for a linear filter, the weight that's applied on a given pixel is always the same. Once you get to the second level, the weight that's being applied on a pixel depends on the activation of the previous layer neuron. You can visualize weights of the second layer, and they look like this, but they're not very interpretable. And again, they're acting on top of those first layer weights as well. So in fact, some of them, each input's actually looking at a set of filters that's in general different. So it's very hard to interpret these. And I guess I won't jump out here because I don't want to lose the slide presentation. But you can look at some nice demos online, which are in JavaScript, which will show you different ways of organizing the image. There's a t-SNE representation of the digits over there. There's an interactive classification network there on the top right that you can try out to understand how these things work. And similarly, there's a nice TensorFlow playground also in JavaScript that you can try. Excuse me. So let's see. All right, well, I'm going to talk about this next. And again, if you want to look at the videos, it's best to do that offline. Again, I don't want to interrupt the presentation. All right. From the outline we had a few slides ago, there are a few different ways of trying to understand images. One of the simplest ones that doesn't require looking inside the network is to use occluding patches. So if here's my input image, and if you imagine I take a little gray patch and move it around on top of the image, basically change the value of the pixels in those locations under the gray field, and then I can look at the output of the correct class, which would be dog here. I'm sorry, Pomeranian, actually. And that heat map on the right shows the relative intensity of the softmax output that says Pomeranian. Okay, so the coordinates of the right map show the center position of the gray rectangle, and red is positive and blue is negative. Or, sorry, red is close to 1, blue is close to 0 in this heat map. So in other words, if I move this gray square up here or over there, the intensity of the Pomeranian output is very high and close to 1. If I move the gray rectangle right over his face and cover his eyes and nose, the softmax prediction for Pomeranian shrinks and goes much closer to 0. Is that making sense? So from this perspective, I can say that, without even going into the network, the critical parts of the image in terms of this network interpreting the image as a dog, a Pomeranian, are these areas here, basically around the dog's face. Okay, excuse me. So that one's pretty easy to see what's going on. This one has a label of car wheel, and the heat map here shows it. If we occlude around here some of the trim of the vehicle, it has a modest effect on the label. If we occlude the wheel itself, though, once again, we drive down the label probability dramatically. And finally, there's an Afghan dog in here. And when you cover this part of the image, you see the accuracy dropping once again. All right. So, it's somewhat promising, but also fairly obviously pretty limited because it doesn't tell us. The resolution's very coarse. We're only moving this big patch around. And we probably have to include lots of different, basically all of the strong cues for the classification if we want to have an effect. Yeah?
Just to clarify, each pixel in the right side corresponds to a different position of the gray.
Yeah. Each pixel on the right is a position of the center of the gray mask. So the scale's been, I think, slightly tweaked, or maybe it runs off the image. I'm not really sure.
So do they essentially in this experiment, do they take that block, that gray block, or essentially the mask of the image?
Yeah.
And they feed it through a network and then plot its probability?
Yeah, that's right. So every pixel here is an end-to-end run of the convolutional network to get a label. Yeah. Was there another? Yeah.
So blue means covering up that place affects the accuracy, but does the red mean it improves the accuracy, or just?
No, it's just false coloring, so that blue is 0 and red is 1. And the softmax output should be between 0 and 1. So red is sort of normal. Yeah. Yeah, it's interesting. Some of the, for whatever reason, even covering up some of the people seems to have an effect in the bottom right image, which is kind of strange, but yeah. Okay, so that was an image-based approach, meaning we only did things to the image. We didn't have to look inside the network. Generally, we can get a lot more information, though, if we do look inside the network. So those are called network-centric approaches. So here we like to answer more precisely which pixels from the input image have the biggest effect on the output. So one thing we can try is pick, let's say, the output of the network where we've got softmax scores, or right before the softmax where we've got linear scores that should be highest for the correct class. So we can pick a class like Pomeranian and then run an optimization over the set of images and basically compute gradients in image space of the output label, and then keep increasing the pixel intensities in the direction, or decreasing, changing the pixel intensities in the direction that that maximally improves the label. All right, so hopefully it'll help a little bit to write that out mathematically. So we have a score function, basically for class C. So if you like, this is the value coming out of this predictor right before the softmax. So we maximize over I the score, and it's argmax, meaning we maximize and then remember what the image was that caused the maximum. And then there's a regularizer here which says that the image shouldn't be too large, because in a network that just has ReLUs plus linear layers, basically the output intensity can be unbounded. The output, output activation can be unbounded. And if you multiply the image intensity by k, the output intensity will normally increase by k as well. Is that quite true? It's not 100% true, because if ReLUs can interact with bias. But generally speaking, there's no bound. So anyway, introducing that L2 norm on the intensity of the images will make sure that the images are not, have excessively high intensities. Okay. Yeah, the L2 regularizer has a particularly nice property in terms of linear layers. So for instance, for the first weights, the image that maximally activates the output of a linear filter is the weights of the linear filter. You can sort of do the math actually fairly easily. You just differentiate that thing and you'll find that the input image is the the filter weights themselves are the maximally activating image. So L2 regularization is kind of special. It shows you effectively what what the gradients are of a given cell with respect to the inputs at that activation level. Excuse me. Okay, let's see. All right, so yeah, and so you can iteratively improve this image by backpropagating the gradient. Hopefully that's intuitive. We're trying to maximize an image intensity. So if we compute gradients of the output with respect to the image intensity, that will improve the output. All right. And so it's similar to stochastic gradient, except that we're optimizing an input image instead of network weights. Okay, and drum roll. This is the kind of image that you get. So maybe you can recognize in general some of the things. There's dumbbell-shaped cup. You can see perhaps some traces of cups in the input image. And this is for an AlexNet. Dalmatian, you can see sort of parts of a Dalmatian dog, but generally a little bit, well, psychedelic could be one word to describe it. Not really close to a faithful image, but still perhaps promising. So there's some reasons why these look so, what's the word, so mixed up. Anyway, but still they might be enough to give you at least some intuition of what the cell's responding to. So there was some follow-on work by Yosinski and al. And they were trying to make those images that we just saw a little bit more interpretable. So they noticed, for instance, that there's a lot of high-frequency spatial noise, so things that appear very, what's the word, like a grid of lines. So they applied a penalty, a regularizer to that. And also there are a lot of pixels that have very weak values, and so they just clip them back to 0. And yes, all right. They basically, all right, clip the pixels in 2 different ways. All right. So applying those tricks produces somewhat more compelling images. So you can see now the flamingo images look like some kind of cluster of flamingos. Pelican looks pretty good. Hartebeest, which I guess is some kind of antelope, I think, looks reasonable. And station wagon, maybe. Anyway, so it's a considerable improvement. And again, it's just using some somewhat heuristic methods to improve the visualization from the previous method. Okay. But there's a kind of an intrinsic problem here, which is that, as we'll see in a moment, these classifiers, and in fact the human brain as well, they have 2 kinds of input from other neurons. One of them is excitatory, meaning that, you know, the cat is a cat because he has paws, a face, eyes, ears, etc., or she. So there's a kind of an additive conjunction of features that comprise the cat. So when you backpropagate, you should highlight those features. But a more subtle situation is that the cat is also not a snake or a horse or a table. And the network weakly recognizes some of those other features and uses them as inhibition on the cat image. So really, when you're looking at these back-projected images, you're seeing some of the excitatory features of cat, plus some of the inhibitory features of snake, table, tree, everything else. They're kind of weak, but sometimes they can add up to a fair amount of components. So, all right, we'll address those in a moment. There's one more thing I want to talk about first. So, but the techniques we've talked about so far can be used to at least do a better job of segmenting out the actual object that's triggering the reaction here. So we can do that by visualizing the data gradient. So how does the gradient affect the output again? And if you take a few images and look at their effect on the output, you can see for the sailboat, there's a cluster of white pixels or nearly white pixels, that those have the strongest gradients on the output. Similarly for the dog and for that fruit and some of the other images. And this gradient, you can stretch it a little bit to turn it into an actual clustering that highlights the object. So this is a little bit ad hoc, but what they do here is they take these gradients, which are either typically very weak or quite strong. The problem is that in the vicinity of the object itself, there's both strong ones and weak ones. But you can still produce a nice clustering of the image by using a couple of thresholds, which is what's shown on the right there. So the blue pixels are very strong gradient pixels. The cyan, light blue pixels are very weak gradients. And the red are somewhere in between. And it turns out by doing careful graph clusterings, the red pixels get kind of drawn. The red pixels are sort of undecided, but if you look at their neighborhoods, they get drawn to either figure or ground other pixels. And so doing that produces this image here where the pixels exactly under the grasshopper get identified as figure pixels, and pixels in the background get identified as background pixels. And it successfully pulls out the grasshopper and the snake and the bird. So again, it's a little bit ad hoc, but it does show that the gradients themselves do capture a pretty good representation of the area of the image that's critical for that label, if you process them carefully. All right, any questions about this idea? So sort of same idea, just looking at image gradients, or gradients on the input image with respect to a given label, but more carefully kind of clustering them together. Okay. So, so far we've been computing gradients or optimizing images for a particular output class, but we can also do it somewhere in the middle of the network. So we can pick neurons here or here or here, run the same kind of optimization and try to see what the image looks like. Yeah. So, and here we start, it starts to be beneficial to think about inhibitory versus excitatory relations between networks. Because once you go into the network, there's a whole lot of connections that are arbitrarily, some neurons that arguably are mostly fulfilling an inhibitory role. So you probably want to separate out inhibitory and excitatory effects. So here's the result of doing that. So on the left, if you just backpropagate the gradients from a given cell, you'll get the image on the left. The image on the right is from a method of guided backpropagation where you only go through the excitatory paths. And you can see that it's a lot more compelling in terms of kind of showing you positive features from the cat image, not necessarily, other effects that might be inhibitory. Okay. All right, and so repeating that intuition, neurons, when you have a neuron A that is connected to a neuron B, there's a weight between the two in most cases, at least in weight layers. The weight layers are really where you're mixing connections between different locations in the image and different pixel depths. So each of those connections has either a positive or negative weight. If it's a positive weight, then more activation from neuron A means more activation from neuron B. But if the weight's negative, it's the opposite. And we see that also in human vision and animal vision. So when we're tracing back to find the pixels on the input that influence some neuron, we probably want to do a focus on excitatory. I'm just saying that, and that's the effect of it we just saw in the slide. Because there are, there's a narrow set of excitatory features that the cat image has, right? There are actual paws and ears and eyes and so on. But there's this much larger, more diffuse class of negative neurons like scales, feathers, fins, etc., that have an effect, but you don't really want to know that. If you'd be back propagating, oh, well, there's sort of a negative scales image here, negative scales activation, so it's not very helpful. All right, so how do we do that? Excuse me. So the simplest thing we can do when we're doing these gradient-based calculations is just back propagation. So if we have a forward pass through a ReLU layer, and by the way, it's sufficient to do these kind of calculations at the ReLU layers. So here's a forward pass, and we compute the ReLU output, which has all the negative values set to zeros. In the backward pass, we have some gradients here that are shown here, and then the zeros mask out the values. If you recall, the gradient of a ReLU is 0 at the pixels that are negative, that have negative activation. So basically, after we apply the 0 mask here, we get the same gradients, but the pink pixels are zeroed out, going backwards. So anyway, so the back propagation with a normal ReLU removes negative activations. Guided back propagation, in addition, removes negative gradients. So the yellow, this is an image of gradients here. You can see some of the gradients are negative and some are positive. The normal back propagation ReLU gradient removes the things that are 0 there. But guided back propagation removes negative gradients, because intuitively negative gradients mean inhibitory neurons. So yeah, so you remove those inhibitory connections by adding this inequality here into the equation for the activation going backwards. And among other things, you notice that it makes it a lot more sparse, maybe roughly half as sparse. And it's already considerably, maybe half of the activations are on moving forward, and you take away maybe another half going backwards. So it's another step. And in fact, if you want another variation on this, you can actually do the masking only on the negative gradient. So only remove the excitatory inputs and basically turn off the effects of the ReLU if you want to propagate backwards. So this is kind of very heuristic, but that's what it's called a deconvnet, and it just has this term that's based on the sign of the gradient. So you use that as a mask to go backwards. All right. Yeah, so here are some examples of guided back propagation, which is the last option we looked at. So that's where you mask out both using the ReLU activation and also using the gradient sign. So Yeah, let's see. So the two clusters of image are convolution 6 here. So you take one neuron from convolution 6 layer, back propagation using this guided back propagation until you get an input image. And interestingly, it looks like there's some letters and digits that are recognized here. And otherwise some what look like eyes or noses. And those eyes or noses? I think they're noses, sorry. All right, so over here, by the way, this is a model trained on AlexNet. I'm sorry, trained on ImageNet. And so you can actually look at the patches of image that most strongly activate a neuron. That's another way to understand what the neuron is recognizing. Just find the image patch that's most strongly activating it. And that's what's shown over here for various different neurons. And you can see that, yes, some of them are actually even little substring recognizers, I guess. Not just single digits, but little strings of digits. Anyway, this is convolution 6 layers, and you get really pretty interpretable input values from that layer. Sorry. And even more interestingly is the convolution 9 layer in the bottom, where you can actually start to see some faces in the second row, different types of face. And sure enough, when you look back at the image, you find some image prototypes that look like very good matches. Okay. And there's the deconvnet again. I think I'm just going to keep moving because I'm going to run out of time. So anyway, so using the either the guided backprop or deconvnet, you can work all the way from first layer. First layer, again, it's effectively you have just the actual filter weights, but you can deconv to get guided backprop to get layer 2, layer 3, and I think I showed this in the first lecture, so you probably already have good intuition for this. As you go up in the layers, things are getting more high level. Animal faces, clock faces, and so on. And layer 5 again. Oops. All the way through anyway to the top level where you get entire image classes. Okay. So the process of extracting these maximally activating images is not deterministic in general. Because of the nonlinearity in all of the ReLU units along a deep network, if you initialize an image differently and then optimize to get the maximally activating image for a given neuron, you'll get different answers depending on how you initialized. So if you start with a grocery store neuron here, you find that you actually get this whole different set of images simply in different runs of the optimization with different random initialization. Okay. Let's see. Yeah, so yeah, and there's some methods for doing that initialization represented here in order to get something that looks like a realistic image, because random initialization also will tend to give you somewhat random looking outputs as well. So to actually get an input image synthetically generated that looks like a real image, you have to initialize somewhat carefully so that your initialization is close to a real image, and that's what's represented there. Again, this is showing you the kind of diversity you get at different layers of the network as you go back. All right, so was that section clear? It's just looking at the multimodality of this process of trying to find maximally activating images and observing that it's, there's a lot of diversity in it. And it's helpful to understand what the network recognizes by giving actually a family of strongly activating images. So, so far, we've been looking at the preimages of individual neurons and having some success, but maybe one question we might wonder is, it makes a lot of sense at the output layer to take a class like Pomeranian or dog or something like that and backpropagate to find the images that are highly activating that output. On the other hand, though, once we go inside the network, it's less clear that you should look at individual neurons because it's very possible that they cooperate with each other, that they work as clusters when they're recognizing a given input. There's no particular reason that, if you like, the representations of things should be disentangled. They should be disentangled on the output because you've trained them that way, such that one particular output position of the output vector should correspond to a class. But all of the other inputs are latent. And so perhaps what we should really be exploring instead of individual neurons is families of neurons. So to do that, you can consider a code, which is a set of activations across an entire layer, and seeing what the corresponding input images look like. Okay. Yeah, and you can work either by synthesizing images, or you can look back at images that are from an original data set. I guess this one's actually optimizing over images. Yes, it's yeah, it's optimizing a loss function, which is similarity of an input image relative to the code of some other image with some regularization term. So I think it'll be easier to see on the slide here. Let's see. So, okay. Oh, interesting. Okay. So, yeah. So what this is doing is it takes an input image, goes all the way to the output, or at least the last fully connected layer, of an AlexNet, I think, and then works backwards. So, the image, I'm not sure which class this is most strongly activating. It might be building, it might be site, tourist site, or something like that. But anyway, having the entire code gives the model more information. And in fact, it's able to construct a reasonable looking image. I don't know if you consider this reasonable looking, but it does have the core structure of the dome, for instance. So presumably the word dome is in there somewhere with some weak activation. And even some of the detail of the windows. And again, these are the different recreations of the input image with different initializations. Yeah?
What do you mean by code?
Code just means an entire vector of activations in some layer. So to get a code, you start with an input image, and then you feed it all the way forward. And then it will give you a vector of activations in that last 1,000-dimensional layer right before the softmax. So that's what a code is. So it's got more information than just what is the main class. It's got all these secondary classes, which seem to be enough to capture some sort of core structure. Maybe it's got window, dome, that kind of thing as weak activations. And then when you run backwards, the network is able to optimize and get images that look somewhat like the input image. Yes, and as you might expect, the closer you go, in other words, the earlier the layer that you look at and do this process of going backward from the code, the more lifelike is the recreation, because you first of all got more information, and the information is closer to the input in its representation. So this is the last pooling layer, which means it's the last spatial layer of an AlexNet. So in this layer, the layer itself is still a grid, so it's got spatial information. So if you work forward either from that, is that a Darien? Does anyone know? What is that fruit? All right, doesn't matter. I'll look it up. But if you go forward from that fruit or the, I guess, ambulance, you get a set of activations that are spatial. And then going backwards, it's able to recreate. So for instance, with the bird image, it can actually localize the bird quite well because it knows what pixels are triggering the bird response. Okay. So code inversion works pretty well. And here, if we consider the recreation across layers, here's a recreation from just the output of the first layer, and it's almost the raw image, right? As you, even past the ReLU, there's very little blurring. There's a little bit of loss of accuracy as you go past the pooling layer. But even up to the second convolutional layer, it's really pretty good. So you're not losing much information. And in the second row, you're out now like 4 layers deep, and it's starting to lose spatial accuracy. But before that, it's really quite good. Okay. Yeah, and again, this is multiple reconstructions with the same CNN code, which I think we already talked about. Okay. This is just another inversion approach, so I'm just going to keep going because this is just a technical variation on what we just did. But it does improve the output. All right, so so what if we take this code inversion process and make it iterative? So in other words, we can take a given input image, feed it through the network forwards to get a code, optimize the input image for that code, but then take that as the input image of a next stage of optimization. So in a sense, you're iterating you're iterating the types of image that the network most wants to create. And it's commonly called hallucination, and the tool that does it is called Deep Dream. And probably most of you have seen these kind of animations, I think, right? Yeah. Anyway, so now you know in a bit more detail what's going on. It's a forward-backward process, and it produces images which are rich in the kind of strongly activating mid-level features like eyes. There's eyes everywhere. The network loves to create these eyes. And similarly, produces very beautiful interpretations of the Starry Night by Van Gogh. Or actually, is that, well, it looks like the Starry Night anyway. Okay. Yeah, and it's actually a very small amount of code to do that. I just want to keep going, though. Yeah, there's a little bit of jitter regularization to avoid it from getting stuck. Okay, I need to keep going. The last thing I want to talk about is neural style transfer, which is a very partly visualization, partly image generation technique that's also a network-based approach. So it turns out that the style of an image is strongly captured by second-order statistics. And we can use those statistics to synthesize images that are similar in content to a reference image, but very different in terms of style. And so you can see some examples. This is a styling image here, an original content image here, and the output is a new image which has the same content, but the style of the style image. And similarly here, we've got a variety of styles of this input image here. Okay, a few more examples. And there's online tools that you can use to create these images. Okay, so so from the content image, you generate a set of codes across all of the layers. So far, when we talked about code, we had one layer in mind, and we took all the activations of that layer. So here for neural style, we want to consider all of the activations across the network. And so it's like the total representation of the state of the network. It's a pretty big thing. All right. So the gram matrices are the second-order statistics, or gramians, of the pairwise activations across, so the gramians operate on the different feature dimensions, not across the spatial dimensions. So in other words, you sum across every spatial location the set of activations, say in conv1. Conv1 is 224 by 224 by 64. The idea is to compute the second-order statistics between the features, the 64 features. So that means that you compute this matrix where the V's have dimension 64, and then 224 by 224 is the other dimension. So the corresponding pixels are just linearly ordered in some order, and then you can multiply V transposed by V to get a 64 by 64 matrix that effectively sums over all of the positions in the image. And that's then the style matrix. Okay. So, and then we have a surprisingly simple optimization problem. We have a loss between let's see, X is the image. Yeah, X is the image. P is the content. So you have a content loss between X, the new image, and P is the content image. And then you have a separate style loss based on that Gramian matrix between the Gramian data A and then the synthetic image X. And just as we've seen earlier, the image synthesis from early codes is actually very good. So not surprisingly, we would expect to get pretty good images if we just, for instance, left out the style and we optimized the content layer from all of the codes. We already did that. It looks pretty good. Now, but adding the style loss is going to, change the kind of images that are being generated. The core structure will be the same, because they're being influenced strongly by particular pixel locations, but their statistics are going to be very different. So for instance, a painting, something that's styled as a painting will have much higher correlation between pixels nearby. And so that's enough typically. Oh yeah, and you can do it live actually. So I'll explain this in a moment, but you can actually train networks to learn the style of a particular style and then run them in a feed-forward direction. So you don't have to do this optimization on every image. And that's how this demonstration's happening. So there's a live camera image of somebody coming in and out and kind of bombing the display. But you can see there's 4 different very interesting styles that are being produced. All right, so so the idea here, what we looked at first was to optimize the image such that the code matches the target code and the style matches the style, but that's an iterative process. The second approach was to train an inversion network from the code to the image with an image-to-image loss. And you can, in the process of training that, that synthesis, you can actually use the images from the first method to train the inversion pipeline for the second method. So I don't know if that makes sense, but yeah, basically you can take the synthetic images with a particular style and then train an inversion network to invert to that style. All right, then here's an elaboration of how that's done. Yeah, so the image comes in here. Let's see. Yeah. Here's the style target coming in here as a set of activations. I'm sorry, as a set of, what is this? Fixed GAN. I see. All right, so there's 3 different types of image that come in for training: the content target and the style target, and then the input image goes through the middle. All right, so it doesn't require any optimization and produces a styled image in basically real time. All right, so let's stop there. So we've looked at first the TSNE method, which is a method for doing embedding of high-dimensional data, so we can interpret, the way that the data clusters or affinities between the high-dimensional representations. And then we looked at a variety of methods for visualizing CNN data. The weights on the first layers are easy to interpret, but that doesn't generalize because of nonlinearity beyond the first layer. We looked at image-centric visualization, including masking out parts of the image. Network-centric visualization, at first we were looking at optimizing images to maximize an activation or an output class. We found, though, that can lead to very high-frequency, hard-to-interpret images, so it's important to regularize them. And going beyond just regularizing the input images, we also argued that by discarding the inhibitory connections using a guided backprop approach, you get more interpretable images, which consist more of the positive excitatory features from the earlier layers of the image. And in any of the methods that maximize either a code or a activation of a neuron, the initialization matters, and you can get different results by changing initialization. The full layer activations or codes contain much more information and allow better reconstruction. And, excuse me, you can actually iterate the process of generating codes and feeding them back to create this hallucinatory animation, like Deep Dream. We didn't actually talk this time about fooling images. We're going to talk about those in a few lectures. But finally, we did talk about neural style transfer, which is learning a classifier, taking outputs from a network to generate a content code that you want to match, but also looking at the second-order statistics between different features in that layer to compute style, and then generating a synthetic image that matches the content and also the style. All right, so we'll stop there. This is going to be the last lecture for the midterm. So, material for midterm is up to today, and then we'll start again next week with different material. Okay.